Good afternoon, everybody. Thank you for attending another in our program on the solar system. A personal note here, I may look like I was in a headlock with a squid, but actually it was my dermatologist yesterday. So I've got a few dots on my face. I'm very pleased to introduce Professor Amy Williams, a geobiologist and an astrobiologist in the UF Department of Geological Sciences. Dr. Williams is also Assistant Director of the UF Astreus Space Institute, which many of you may never heard of. It is a new organization at UF, relatively new. Professor Williams studies the formation and preservation of clues of life in extreme environments on Earth, and uses these analog studies to inform the search for evidence of life and organic carbon on other worlds, such as Mars, the Saturn moon Enceladus, and Jupiter's moon Europa. Currently, Professor Williams is a member of the team studying Mars habitability and the search for life with the NASA Mars Curiosity and Perseverance rovers. Professor Williams took her Ph.D. in geology at the University of California at Davis. Please welcome Professor Williams.
Thank you all so much. Thank you, Phyllis, for the invitation to come and speak with you all today. So I was so excited to come back and visit because I was actually here a few years ago. And so if you were also in the audience a few years ago, part of this presentation may look familiar in the beginning, but I promise I have updated it with some of our newest discoveries from Curiosity and Perseverance. And please let me know in the back if I start kind of wandering off with the volume. Please let me know to speak up. So our presentation today is not a PowerPoint, but this is actually a non-linear presentation platform called Prezi. And so it actually enables us to kind of zoom around and kind of explore the different regions of Mars that I'm going to talk about today. So let me go ahead and get started. Let's zoom into Mars here. So I wanted to set the stage by not just talking about the two missions I've had the incredible opportunity to work on, but I also wanted to start with sort of the background of Mars exploration. And so we're going to start with the past, maybe 50 plus years of Mars exploration. So we can actually go further back than our first landed missions with Viking. We can go back to the Mariner flyby missions, which provided us with pictures of Mars that after, basically centuries, like we've always been watching Mars, when we finally realized that these were planets in our solar system, we had this image of another planet with life, with water, this other world that was Earth-like, but red in the sky. And when Mariner flew by, we actually were disappointed in some ways to discover that Mars looked like a cold, dead, cratered, red world. And that view kind of stuck with us for a long time. And actually things have evolved such that we now know that Mars was warmer and wet in the past, in the ancient past. And so that's the story that I want to tell you today, is sort of that evolution from exploring Mars as sort of this cold, dead world with the Mariner flyby missions, and then landing with Viking in 1975. So these were two landers that took us from a cold, dead world to wanting to look for life on Mars. And although we did not find conclusive evidence for life on Mars with Viking, we've actually been able to build our understanding of Mars through a fleet of landers and rovers that we've sent over the subsequent 50 years. And so what I want to pull your attention to here is some of our rover colleagues that have helped us to explore the red planet, starting with Sojourner in 1996. So this was a little RC car-sized rover that went along with the Pathfinder mission. And it was actually a technology demonstration meant to show us that we could operate an autonomous vehicle on Mars. And so that allowed us to take sort of the next big step and send the Spirit and Opportunity twin Mars exploration rovers in 2003. And the point of those missions was to search for evidence of water on Mars. We suspected it had been there from orbital images, but these missions were meant to go in situ, wheels on the ground, and help us understand sort of the history of water on Mars. And they actually found extensive evidence for it. So we know Mars had lakes and rivers in the ancient past. So scooting forward, not to ignore our Phoenix and InSight lander colleagues here, but scooting forward to the Mars Science Laboratory Curiosity mission. This was my first Mars mission experience. And this mission, instead of just looking for water, is looking for evidence of habitable environments. So places where life would want to live if it had ever been present on Mars in the ancient past. And building off of that, we took the next step with the Mars 2020 Perseverance rover to actually look for evidence of ancient life preserved in the rocks of Jezero crater. And so we are still conducting that search, but I have some cool kind of add-on slides today to share with you some of the recent discoveries and announcements that we've made from that mission. So we've gone from searching for water to searching for environments where life would want to live to searching for evidence of ancient life. And I do have down here this ever-evolving heartbreak of mine, which is Mars sample return. And we'll get into this as we get into the perseverance part of the talk. But this is the sort of next step for the samples that are being collected by the Perseverance rover, which was to collect the samples in a rocket, launch off the surface of Mars for the first time, and bring those samples back to Earth for us to be able to use all the instruments on Earth that we can possibly think of that would allow us to answer some of the most profound questions about Mars and also help us to understand more deeply sort of the deep history of Earth. And I have a question mark here because things are very much in flux when it comes to paying for Mars sample return. But let me tell you a little bit about sort of the exploration of Mars. And this is a little bit of a sort of, at this point, memory lane trip for me into how I started my career as a planetary scientist. So this is Curiosity. That's her name. She's a ship, a starship, so we call her a her. Curiosity launched in 2011 and landed in 2012 on Mars, and its prime mission was meant to be 1 Mars year, so that's basically 2 Earth years. We actually have just passed 7 years on Mars, so we are on Sol 4687. So Sol is a Martian day. It's 24 hours and 39 minutes long. And this becomes very important when you first land one of these missions on Mars because we actually live on Mars time for the first 3 months of these missions. So you have the science and engineering teams driving into the Jet Propulsion Lab. If you start your workday at 9 a.m. with everybody else, by the time you start getting through the week, you're moving 39 minutes ahead every single day. And after a while, you end up driving in, at midnight, you're trying to make your cup of coffee. It's not like getting used to working like third shift because you never get used to it. You're always progressing forward by 40 minutes. So Mars time and Sols are near and dear to my heart, and I've done this twice now with Curiosity and with Perseverance. And Curiosity has now driven more than 22 miles in our crater of choice, which is Gale Crater. So let me tell you a little bit about the mission. I told you it's about evaluating habitable environments, places where life would want to live if it had ever been present. And so that means exploring sort of like what are the biological conditions that could have been met to allow life to live there, characterizing the geology and the geochemistry of the rocks, as well as giving us more insight into planetary processes, how the rocks were formed on Mars, and the surface radiation environment, because this becomes important both for searching for evidence of life, ancient life on Mars, as well as the conditions if we ever send astronauts to Mars. And so let me tell you a bit about Gale Crater, our destination of choice for Curiosity. So this is a colored map of Mars. So you have the big volcanoes and Olympus Mons, you have the Hellas Basin down here, and Gale Crater is along the sort of the dichotomy between the southern highlands and the northern lowlands. And if we zoom in on Gale, here it is. It's about 150-kilometer wide impact crater with a 5-kilometer tall mound of sediments in the middle. And this is really useful for us if we look at a higher resolution image. This is really useful because each of those layers preserved in that mountain are like pages in the book of Martian history, at least for Gale Crater. And we were so interested in exploring this area in particular because the rocks seemed to record a shift from one where there was abundant water to a far drier climate. And that's some of the data that I'm going to show you today and sort of the rocks that we're exploring right now. So in the past, we know that there was water flowing into the crater and pooling down here at the base of the mountain. And that's sort of where our entire mission started. So let's back all the way out here. One of the really incredible things about Curiosity is how you get a vehicle of this size to Mars. Our previous Mars missions used sort of the, what would you call it, a balloon or like bags full of air that would allow you to land like an airbag landing system. But Curiosity was far too big. And so we had to design basically this rocket pack that goes on the back of the rover and allows the rover to drop on a tether until all 6 wheels touch the ground. And then the rocket pack disconnects and flies off and tries not to crash on top of your rover. And just for some scale, here's some folks in bunny suits in the high bay at JPL with Curiosity and with them stacking the Sky Crane system on the back of the rover. This is, at this point, science fiction. You can't test this from start to finish on Earth. Our atmospheric density is different, the distance you're going to travel, the gravity, the way that gravity is going to affect the payload. And so the first time that this mission or that this landing system worked was when we landed on Mars. And so this is the JPL mission ops room celebrating our actual landing. So that's what it takes to land a vehicle like this. And that was a huge step forward in our ability to land really large vehicles with really robust payloads. And so I try to pull together all of our discoveries from the past 14 years into one slide, which is very difficult. But what I can summarize them as is saying that we found abundant evidence for liquid water in the past in Gale Crater. So this was right as we landed. We have this kind of rock that's called a conglomerate. And there's an image on the right that shows you what it looks like on Earth. And there's an image on the left that shows the exact same kind of rock that we landed on when we landed in Gale Crater. And this kind of rock with pebbles embedded in it tells us that there was a river flowing into a lake in this environment in the very ancient past. And that the size of the rocks actually tell us that the water was maybe ankle to knee deep. So we have a sense for how fast that water could have been flowing, what the discharge would have been, which is really exciting for starting to pull together, was this just like these little ephemeral pools of water, or was this a more robust hydrologic cycle? And it seems like it was the latter. We've also found in almost every sample that we've collected suitable environments for life as we know it. So this is showing a subset of the drill holes that Curiosity has made into the rocks. Curiosity is not collecting samples. We actually drill the samples out of the rock and ingest them into the instruments inside the rover. And this allows us to perform our in situ analyses. And we find in almost all of these environments evidence for water in the ancient past, evidence for an energy source for microbial metabolism. So this would be life like our bacteria that's able to extract energy from these little 1-electron transfers from the rocks and minerals in the subsurface. And we do also have evidence for organic carbon preserved in the rocks. And that's sort of the third pillar of looking for habitable environments. So here's one example of an organic molecule that we detected in one of our drill samples. So you and I, we're made of organic carbon. All life as we know it is made of organic carbon. Finding organic carbon on Mars like this does not mean that we've found life, unfortunately. What it does mean, though, is that the building blocks for life were present, and they're not destroyed in the near surface by that radiation environment. So there's probably a lot more organic matter there originally, and is slowly being decomposed over geologic timescales and exposure to these radiation environments. One of the cool things that we've explored as far as potential biosignatures, things that people want to know, like, could life have made this, is actually the methane that shows up on Mars. We get these interesting plumes of methane. And that can sometimes come from like volcanic activity, but we also know on Earth that life makes abundant methane as well. And so what we've discovered is this really interesting sort of unexpected cycle of methane formation. Why is it there? It should be breaking down very quickly unless there's a modern source for it. And so we're starting to learn more about how sort of the air circulates, at least in Gale Crater and in certain parts of Mars, that allows for that methane to kind of get belched up from the subsurface before it dissipates. And so there's a really interesting sort of evolving story of methane on Mars. As I mentioned before, we were talking about radiation health risks for human astronauts if they eventually go to Mars. And we know that there's now evidence for a thicker atmosphere and more water in Mars's ancient past. And this is just a couple of frames stitched together, and it shows clouds passing over the mountain in Gale Crater. And I think this is one of the really lovely things, like if you've ever been camping out west and the sun has set and you just have this slightly back illuminated movement of clouds. It's a very terrestrial little image here, but it's completely on an alien world. So that's sort of the summary of things that we've been working on over the past 14 Earth years on Mars. And I wanted to kind of tell you a bit about what we've been doing recently with the mission. So this is one of my favorite images of the mountain that we're climbing up. We informally call it Mount Sharp. And you might notice the sky in this image is blue. The sky on Mars is not blue. It's sort of a salmon pink red color. But as a geologist, having that color balance and that blue background actually makes my eye more readily pick out details in the rock that I would miss otherwise with that background Mars color. So I really enjoy this because it looks like any other mountainous terrain you might see on Earth, but it's on Mars. And so we've been traversing up the mountain, and we're just a little bit below sort of this light-toned material you see here, but we're actually kind of off the page now, and we're further over to the right on this image. And so if we zoom in to sort of the base of that image, this is a way of looking at our traverse once we got off of the crater floor and started climbing the mountain. And so the white line is showing you our traverse through material that has a lot of clay in it. And so we know that that represents an environment that was wetter in the ancient past. And up into this orange-yellow unit, which has a lot of the sulfate minerals in it. And that represents a drier environment. And so we recognized even from orbit that what we were seeing here was a major environmental transition on Mars, from the warmer, wetter Mars of the ancient past to that drier, colder world that we're more familiar with today. And I don't even have an updated image of this, of our traverse line scooting over this major outflow channel, but we've actually been moving on this image over to the right. And this is roughly where we are now, because what we see here, if we zoom in, is this really incredible texture that we've seen from orbit. We saw years ago when we were deciding if we even wanted to go to Gale Crater. This is called the boxwork terrain or boxwork structures. This really distinct feature that we see from orbit. And if I zoom in on it, this is actually one of our more recent pictures from the rover that shows us looking at sort of that ridge and hollow structure, and you can see it repeating over here on the right-hand side of the image. So if I go back, you can kind of see that structure from orbit represented in the ground image here. I think it's just something I've been looking at since I was a graduate student, and we're here now actually getting ready to drill into the rocks is pretty exciting. And this is really cool because these features, we believe, formed in the subsurface from groundwater, moving through the rocks and cementing the rocks in place. And so the sort of the fractures between the rocks were cemented, and that's what's now the raised ridges. And the material that was in between those has now eroded away, and that's where we have the hollows. And this is a really extraordinary opportunity to explore an ancient subsurface environment that also could have been habitable in the past. We now know that microbial life like bacteria and archaea live deep, deep in the subsurface of Earth, kilometers down, eking out tiny, their existence, growing and living very slowly. And then we have the hope that if there was ever life on Mars, perhaps it also went into the subsurface. And that's why this is an exciting sort of place to explore where that life might have been at some point in the past. So again, this is all very speculative, but it's looking for these environments to sort of drive us to understand where would life have wanted to live on Mars in the past if it had been there. So we're going to zoom all the way out. Our ascent of Mount Sharp continues. We'll explore the boxwork structures, and then we'll move up towards sort of the base of this light-toned, it's called a Yardang unit, a unit that's been shaped by the most predominant force on Mars today, which is aeolian, or wind erosion, as it starts slowly kind of pulling grains away from the rocks. So let's scoot all the way back from Curiosity, and I want to take you to sort of the next iteration of Mars exploration, which is the Perseverance rover. So you'll notice that Perseverance looks an awful lot like Curiosity. It turns out it's much cheaper to build the same vehicle you've built before. You don't have to put in all of the new studies to develop a new bus, to develop a new landing system. So the rovers look similar, but there are certainly improvements. We have much better wheels on Perseverance. We have a different suite of instruments, and we have the ability to collect samples. And so I apologize that the closed captioning is covering some of the goals of this mission here, but one is to characterize geology. Oh, it's okay, it's okay. I remember what they look like. Characterize geology in the environments where we think they were habitable, where life may have lived in the past. We can characterize the rocks for sort of their astrobiologic potential. How likely is it that there was ever life that could have lived in these rocks? And we have the ability to then collect those samples with the hope of returning them to Earth at some point in the future. And so our mission specs are a little bit different for this mission. So we landed in 2021. We're currently on Sol 1647. Our prime mission, instead of 1 Mars year, was 1.5 Mars years, and we've actually driven further now than Curiosity has, over 23 miles. One of the other things that's listed here is a helicopter log. So just like the Sojourner rover in 1996 was a demonstration that you can drive an autonomous rover on Mars, we sent a helicopter called Ingenuity to prove that you could conduct powered, controlled flight on another world. And we were supposed to fly 5 times for the tech demo. We kept flying further and faster and higher, and we kind of crash landed after 72 flights. But that was the point at that stage, to see how far could you push it? Where does the technology need to go afterwards? And the vehicle actually still has power. And if we ever drive back that direction so that we can communicate with it, we can downlink some of the images that it took while it was sitting there. And so I said that we're collecting samples for the hopeful return to Earth at some point in the future. Right now we have 26 rock cores, 2 samples of regolith, or sort of this dirt-like material, but as a geologist, I would never call it dirt, and an atmospheric sample. And we've depoted 10 of these samples so that in case something happens to this vehicle, we actually have a contingency cache of samples. But what you'll end up seeing as we go into talking about, where we've collected samples, the complete sample cache on board the rover is incredibly compelling for return to Earth. And if you want to move the closed captioning down, I think, yeah, we should be good. Okay. And then you have to, can you Let's see if it'll do it. If you click on the slide itself. Oh, the presentation. There we go. Okay. Can we try scooting it down again, and we'll see if it'll talk with me. So let me show you where we are on Mars now. Okay, so just click on Mars. We'll see what happens. Yep, it's working. All right. So we are again on the crustal dichotomy, but we've moved sort of up to the north a little bit to Jezero crater. So this is Jezero. It's a 50-kilometer wide impact structure. And instead of a big mountain in the middle, what compelled us to go here is actually this feature I'm going to zoom in on. This, at higher resolution, you might be able to tell is a river delta. So it is a feature that forms when you have a river flowing into a standing body of water like a lake. And so even though Jezero looks like this today, in the ancient past, we envision it looking more like this. With an inlet channel, the delta would be sort of underneath the lake here. And then there's actually an outflow channel that comes out from the southeast of the crater. And so we know that this was a place that had a lot of water in the past. It presents a habitable environment in the ancient past and a great place to search for that evidence of life on Mars in the past, if it ever was there. So let's zoom out. And so I want to tell you about some of the samples we've collected and then get into sort of our full sample cache. And so I told you we went to Jezero because that delta structure was there. And so on Earth, river deltas are habitable environments, lots of water, lots of energy, and a place where you can actually kind of concentrate evidence for life. If it is, little bacteria, they can get concentrated in some of the rock layers you have at the bottom of the delta. If it's organic carbon, that also likes to stick to clay minerals, which tend to get sort of concentrated down in the delta. And we actually saw that from orbit, different types of clays shown in the colors on the delta here. That blue purpley color, the iron and magnesium smectites. Smectite clays are really great for binding organic carbon. And so that's one of the sort of sites we wanted to explore to see if there was any evidence for potential biosignatures, maybe ancient life. And so we landed on the crater floor, we explored down here, and then we made a beeline to the front of the delta, right here, delta. And so if we zoom into the delta front, this is sort of a snapshot of where we were in our delta front exploration. We spent more than a year exploring the crater floor, which turned out to be made of volcanic rock. And so this is actually really fortuitous because if you get those samples back on Earth, you can perform absolute dating on them and figure out exactly when they crystallized from that lava and exactly how old they are. And so that will give us a constraint on when that water was flowing on Mars from the delta rocks. But what was really cool, what we saw here, were some of our first sedimentary rocks instead of volcanic rocks. This is one of my favorites, Kodiak. It's a delta remnant that sticks out from the front of the delta. We start seeing our first low-lying sort of sandstones and mudstones. And as we get up into other regions of the delta, we see like actual muddy siltstone mudstones that are able to preserve some evidence for organic carbon. So these are some of the first places that we explored on the delta front. And on the next slide, I'm going to show you sort of a way of capturing all of the samples that we were able to explore from both the crater floor, which you see on the far right here, and then you see that white line I showed you in the animation where we drove around and went to the delta front. And you see all of the samples that we collected from the delta front as well. And so you see for most of these, actually for all of these, there are duplicates. So we took 10 of these and we depoted them right here on this flat area in front of the delta. So that was the contingency cache in case something happened to the vehicle. But since this time, we have all the remaining pairs on board. Since that time, we've actually collected so many more samples that actually make the cache on board even more valuable. And so that's what I want to kind of pivot to next. Let's back away from the delta. So I want to show you what is, I believe, our most up-to-date sample suite. So this is everything that we collected. This is what's depoted that I just told you about. And then these are the samples that are on board. And so it's showing you what the rock looks like, what the abrasion looks like. So we have like sort of an abrading tool that gets into the rock and lets us look at what the real rock texture is like. Turns out Jezero is a really dusty place. And as a geologist, it's kind of embarrassing for me to say, I don't know if this is sedimentary or igneous. Maybe for normal people, you're like, who cares? But for me, that's an embarrassing thing. And it truly is a challenge to be able to tell in a place that has had dust accumulating for literally billions of years. And so what you're looking at is the traverse from the delta, from the crater floor. There's that loop we went over. Here's the delta front and the samples I showed you before. And then since then, we've been traversing up over the delta, up this river channel, and out of the crater. And we actually are further south now than even these are showing you. And so what I want to show you is a more recent announcement and publication that's come out of this work. And so we're going to zoom in near sample 28 here. And this is going to be, oh, can you click on the slide again since we moved the caption? Nope, just click wherever you want to put, that's fine, but click on the slide because then it will let me move. Perfect, thank you. So we just zoomed in to sample 28, and I'm showing you sort of the landscape and where we traversed. So we drove in along the white line, and we took a detour up to this really bright material that we named Bright Angel, like the Bright Angel Shale in Grand Canyon. And so we're actually interested in sort of the little yellow triangle that's up here, and you can see the landscape image and sort of match these up between Shiava Falls and Apollo Temple here. That's what you're seeing way up next to the edge of this mountain, and that's where we're going to go next. Can you click on the slide again? No, don't move it. Just leave that there. Just click on the slide because otherwise the clicker doesn't work. Perfect. Thank you. Okay, down to the higher resolution image, this outcrop. So this is where we abraded 2 parts of the outcrop, and then we actually collected a core, because if we zoom in, what we see are these little tiny, what we called leopard spots. These little tiny features contain minerals that if you saw them together on Earth, you would know that life actually made them form. There's also organic carbon present in these rocks. So we followed all the protocols. This is what the mission was meant to do. And what we published was a statement that these represent what is called a potential biosignature. As an astrobiologist, let me point out, it is not a definitive biosignature. It is not clear evidence for life. What a potential biosignature is, and this is what I would do on Earth, even if the stakes were a lot lower, is recognize that this is a substance or a structure that can be evidence for past life, but it requires further study to make that confirmation. And I say this because you imagine this rover, it costs $2.5 billion. It's not cheap, and you have 10 plus instruments on board. You know how many instruments we have just in the geology department at UF? Far more than 10. So your ability to come to a conclusive answer with the instrument suite on board, we never intended that for this mission. This mission was always meant to find the most promising samples, which we did, so that we could bring them back to Earth and apply all of the instrument suites that we need to answer these profound questions. When was water flowing on Mars? Did it have the ingredients for life? Is there evidence for life preserved in those rocks? And so this is the most recent thing that has come out, I think, on September 10th. And so this was actually, a big public statement and release that NASA made when the paper came out. But the discovery was made more than a year ago. And we went through the peer review process to have it all published and had reviewers give us, their very strong opinions on these things. But this is, again, I would stand by this, that this fulfills the intent of having a potential biosignature, something we can't confirm unless you bring it back. But man, if you saw that on Earth, you would know life made it. And so with that, that's like sort of our highest or most recent discovery that we've been publicizing from the mission. I'll leave you with sort of this final push, which is that these samples were collected with the intent to return them to Earth at some point with Mars sample return. Mars sample return is no longer funded underneath the current budgetary restrictions of our time, which is hurtful to me, personally as a taxpayer. But I also recognize it was a very expensive endeavor. And so right now, as all of this is sort of getting sorted out, however the chips may fall, perhaps astronauts will pick up these cores at some point. They've been very carefully characterized. The astronauts wouldn't have to walk the 23 miles that the rover has to get these samples. That is a possibility. That's also very, very far in the future if it happens. And so this is my only platform to say that this is where the science, unfortunately, maybe ends unless we can get these samples back. But there's so much exploration still to do. We're still collecting samples, and now we're exploring outside of Jezero in the most ancient terrain that a rover mission has ever explored on Mars. And so this is still a very exciting time to work on the mission, and I still want to leave you with sort of that optimistic view of what science and exploration, responsible exploration, can accomplish. And so as an astrobiologist, let's step back from this exploration. Let's step back to Mars. Can you move the thing down to the bottom? And then can you click on the slide? I'll leave you with a thought that sort of motivates me, which is a quote from a book that Carl Sagan wrote, which is that the universe is a pretty big place. And if it's just us, it seems like an awful waste of space. Thank you all so much for joining me today. I'd love to take questions.
What an amazing presentation. You are A++, the best, the best.
Can you leave me a review on ratemyprofessor.com? That would
Oh,
be
absolutely.
helpful.
Thank you. That's fascinating. What caused, or what do you think caused the planet to dry up?
So Mars is about a third the size of Earth, and it doesn't appear to have ever had plate tectonics the way that Earth does. So that is driven in part because we think that the size of Mars meant that the internal geodynamo, so basically our rotating core, generates our magnetic field that protects us. And without the geodynamo rotating, without convection in the mantle, you don't have plate tectonics, and you eventually lose your magnetic field, which means that you no longer have protection from the solar wind that winnows away the atmosphere. So when you don't have an atmosphere, you don't have a way to retain those volatiles like water. So the planet, that's why it dried out. It clearly did it a long time ago. That's part of what sample return would enable us to get absolute ages on, is the age of the rocks when they formed sort of in that stratigraphic layering. So that can tell us more about when that process maybe occurred. We think it's pretty early on, but again, it's like, what's it called? Comparative planetology, where you're trying to use lessons on Earth to say, okay, when might this have happened? So we think that boundary is maybe 3.8 billion years ago. I mean, put your big error bars on there. So quite a long time ago, but we don't know with certainty. And it was almost certainly a very, long-term process as well. It didn't just happen overnight.
Thank you so much for allocating time to give us some appreciation for what's going on there. I have first a clarification and then a question. Okay, in terms of the clarification, did I understand you to say that you have confirmed that there is astrobiologic potential, which is potential for life? Did you say that?
There is the features we identified are characterized as potential biosignatures, meaning if you saw them on Earth, you'd recognize life had a role to play in them. But without additional information, we cannot definitively say that on Mars.
Okay, I want to push you a little bit.
Yeah,
push you just a bit. And it's unfair to push a scientist like this, but do you think there was actually life on Mars?
I love this question. So, as a scientist, I do not yet have the evidence for that. I do find the evidence from Mars that we have been building to be compelling in the sense that Mars is far more complex than I think we initially wanted to give it credit for, I guess, if that makes sense. It has all of the nuance that we recognize Earth having, potentially without life on the surface. So we do not have evidence for it. If life arose on Mars, if it occurred around the same time it arose on Earth, both planets were warm, wet worlds at the time. It's possible. We had the same influx of planetary materials and organics. So it's possible life arose. Is it still, if it did arise, is it still there? If it's there, it would have to be deep in the subsurface, protected from radiation where there's still liquid water, and the possibility of like metabolizing and have like eking out an existence, sort of like our really deep subsurface microbes on Earth. So as a scientist, no, I will say we don't have evidence. As an optimist, I would say the universe is a pretty big place, and if it's just us, it seems like an awful waste of space.
One final question. What is the temperature on the surface of Mars?
So at the equator, close to the equator where the rovers are, it does every once in a while get above freezing. I think it almost got up to like 70 Fahrenheit once, like on a very warm summer day. But normally, I mean, every day you cycle down to below freezing. At the poles, I mean, you're looking at negative in the hundreds, and especially, in the winter. So it actually, even the winter in the equator gets so cold that we run our survival heaters on the mission so much that it actually impacts the amount of power we have to do science. So it does get very cold, but it does occasionally rise above the freezing point on Mars at the equator.
I think one of your diagrams pointed out methane clathrates, which is
Well,
frozen methane.
Yeah, frozen methane. Mm-hmm.
So I've also read somewhere, my brain is saying, perhaps it was a speculation that there was subsurface water ice on the poles.
Oh, there's water ice on the surface at the poles.
On the
So there's
surface of the poles.
definitely still water ice present, and there's water ice in the like what were the aquifers in the subsurface. As you get closer to the equator, you have to go far deeper to be able to access that. You might be in bedrock where you don't really have aquifers. You just have like sort of like fracture with some water in it. But there's certainly still water ice. The problem is you don't often meet the temperature pressure triple point special space where you can have liquid, solid, and gaseous water all be available like you do on Earth. But so for the methane clathrates, that image was showing you sort of a model for like, I think if the captions had not been at the bottom, you'd have seen microbes, ? So it was showing you different potential avenues for generating as much methane as we're able to see from orbit, but on these really random episodic timescales.
Well, we do find very simple, like archaea type life deep miles down in Earth sediments. So it's possible that it's buried in Mars.
And that's what I was referring to with the previous question, that certainly we know kilometers down that there's life eking out an existence. So it's certainly not beyond the realm of possibility for Mars.
I heard Carl Sagan speak, and it was at the University of Chicago that I heard
As
of
inspiring as my talk today. No.
because it was quite amusing because what he said about life on Mars was he said, suppose the Martians sent a rover to us and it landed in the middle of Burton Judson Court, which is one of the dorms at the University of Chicago, and it would come back just a bunch of lowlife.
There's no intelligent life here. Yeah, I've seen that one.
Is that your contribution to this discussion?
I found that
I know
very
you can do
valuable.
better than that.
Another one is Percival Lowell. What would he think about your evidence?
He was just trying to see if there was water on Mars, right? Like just trying
Well, he
to
was
characterize.
he believed that there were canals, that actually there was intelligent life that was living there on Mars.
There was, yeah, Schiaparelli saw the canali that became the
Right.
canals, and then Lowell like took it the whole another level of like trying to track all that down with the water, and were they like aquaculturing, they're trying to conserve the last of their water.
Right.
Yeah, I mean, I think going from the era that you're describing, like Schiaparelli and Lowell, and like this vision of Mars prior to actually getting there, you know, I would say in person, but as close as we got with our orbiters and then our landers, I mean, you're seeing a very different world than our imaginations originally painted. But I also find a lot of synergy with the original ideas because, you know, we're creatures on this planet. We see our planet and how it functions, and you can apply so much of that to Mars, even the Mars of today.
Well, see, in Lowell's time there was canal building too. That was a factor in factoring in the Mars situation with canals and mistranslating the Italian, which meant channel.
Okay. Got a couple of scientists here.
Oh no, okay.
So you didn't find any ruins of the city of Helium? But I was curious about what's with the highlands? I notice you're in the lowlands, and I can see why. Water runs downhill. But what's the history of the highlands? Why is it so different in the south?
So, okay, yeah, a couple of different things to point out there. So we're on the dichotomy where we're actually we're not nearly as low as you can go where Viking went. Part of that is that the atmospheric density is so low, it's really hard to slow your vehicle down on entry, descent, and landing. So we try to land as low as we can because it gives you a little more time without having to like lose your delta V, slowing down before trying to land. So why is the dichotomy there? If I knew the answer, I could probably win a major award. But our best guesses are in part that because we don't have plate tectonics and we don't have sort of this cycling or circulation within the mantle that you see on Earth, you probably have one big hot spot and sort of then you are like losing heat on the other side. And so that's part of why we think you see the dichotomy, but you also see, so I say there's no plate tectonics, but there is like tectonic features, like sort of rifts and splits, because if you have heat on one side and not on the other, you're going to have some changes in the geometry that make things rift apart or kind of crunch together. So we think that there might be something to do with sort of like the dichotomy being sort of a hot side and a cold side of the mantle that is enabling sort of like upwelling on one side and on the other. There may have also been a really massive impact that sort of like reduced, like on the northern side, that reduced a lot of that in a way that the southern didn't experience. Although the Hellas Basin, which I showed you on the map, is I think the deepest basin on a planet in our solar system. So that's a pretty major impact as well. So if I had the right answer, it would be very special. But these are some of the concepts that we have for explaining that dichotomy and why it's not a bit more homogeneous, like you might expect with plate tectonics.
Fascinating and disappointing that you probably won't be able to get some of those samples back that have potential biological origin.
I'm optimistic.
Okay. What about now that you know that that compound exists on Mars? What about sending an instrument that could analyze that on Mars, so you wouldn't have to bring the sample back, but rather send an analytical tool there?
So the challenge in doing that I have learned doing this for when they land, I don't know, 12, 13 years, is that you can send your best suite of instruments. And by the time they get there, after all of the preparations required to become space ready, to go through technological readiness steps, to fly and survive, your tech is going to be maybe 10 years out of date. And what I have found, so if you have something where you know what you're looking for and you can build an instrument directly try to assess that, you might have more success in like if we send it just to Bright Angel and we look just at those leopard spots, and you have a gas chromatograph mass spectrometer to look at the organic material and see if it had to do with life, maybe you could get at that. But I found the ability to manipulate samples in flight on Mars is still limited. The ability to you would probably want to sample that whole outcrop, grind up that material, and concentrate the organic matter in it in order to be able to detect something that's probably like such low concentration that I would think there would be a challenge to detecting it with an instrument. So we still have those limitations in miniaturizing instruments that can reach that level of precision. And so that's part of the challenge of why not just send something there. We had this opportunity with Perseverance. We had the opportunity to revisit some of these features that look like terrestrial stromatolites. So basically rock features that are formed by bacteria growing and getting sort of encased in the rock. We had the opportunity to go back to a place that Spirit explored that had those features. And we decided to not go back to Columbia Hills and instead to go to Jezero. So I think that there's also a push for going somewhere new as opposed to returning to something that is very compelling. And so I think it'd be challenging to even get that mission to go where you want it to go, because that's the experience we had a few years ago with Perseverance.
The slide on which you have the Gale crater, it shows blue where you do describe having been water, but then the flatlands outside of that are also blue. I mean, was there actually, do you think, an ocean?
Oh, so I mean, I just colored that in to sort of show it where water flowing into the crater would have pooled.
Yes.
Actually, all of the layers, even up to where we are in Gale now, several kilometers up, like vertical distance up, shows evidence for having been deposited by water. So actually, we believe that Gale Crater, it's more than 5 kilometers deep, but that's how tall the mound is now. We believe that that crater was completely filled in with sediments laid down by lakes and rivers. And then actually a lot of that has been eroded away, and that's why we can see the mountain the way that we do now. So it was actually filled all the way up with water deposits. So we see some that are clearly from lakes and rivers. So the question does exist whether there was a northern Mars ocean, and I haven't seen compelling evidence one way or the other, so it's still for me a question mark. There's certainly a lot of water.
The explorers seem to stay on the approaches to the highlands where there's exposed rock, and rather not going to the area that is described as on the slides as being flat. That's why I was asking the question.
Okay, yeah. So the northern lowlands, I think like as you're going from that topographic change, it's sort of coming off of any like mountain range down into lowlands kind of concept, where as geologists, I want to see rock exposure. And so I want to go where there might be stratigraphic context and rock layers to explore, to deconvolve sort of the environmental conditions of the past. Okay. On the ground, like where Viking was, it's sort of like boulder rubble fields, and it's way harder to determine geologic context from that.
So there is presently no atmosphere, or a very thin atmosphere.
It's like 1% of our atmosphere, 1%, 10%.
Is there any
order of magnitude?
Is there any evidence in the mineralogy that there once was oxygen, which would imply life?
Oh no, so it's almost always been CO2 dominated. Yeah.
Okay.
And you had a hand back over here. Don't want to cut you off, Drew.
Another scientist.
Thank you very much. That was wonderful presentation. I was just curious, how deep do you think you would have to go to look where any possible microbial life would be protected from radiation? And would that be a possibility?
Yeah, so We think that if you are 2 to 3 meters in the subsurface, you should have pretty good protection from everything, including galactic cosmic rays. So you should have protection at that level. When it comes to microbial life, so if you're looking for extant life, something that's still living, you also have to contend with the temperature, still that shallow, and the availability of liquid water. And so those conditions are generally not met in the near subsurface. And it sort of depends on where you are as to how far down you would need to go in order to sort of get into a range that might be conducive to, if there was still life, if you could detect it. So yeah, I'd say further than we're able to drill. Right now, the deepest we've drilled is about 6 centimeters. So yeah, we have a ways to go.
So what do you think of Elon Musk's AI hallucination that we could have a colony of humans on Mars if they could get there in the first place, alive?
So I think that the last part is very important that you just pointed out. Our R&D is not there to necessarily get humans there alive on the trip. And we've never launched off of the surface of Mars. So then you don't have any demonstration that you could bring them home, which I think is pretty bad for morale. To say the least. Yep. So I think that support for science and technology will enable us to pursue the R&D requirements to enable humans to make a 6-month trip to Mars, not kill each other in that little capsule. And so actually when you go to space, if you go on a boat, you have to get your sea legs, so you'll be sick for a little while. And then when you get off of a boat, after an extended cruise, you have to get your land legs again, right? So the same thing happens in space. The astronauts are pretty sick for a bit when they get used to low Earth or gravity or no gravity. And then once they got on Mars, they're going to be sick for days trying to recuperate as you get used to gravity on your body after 6 months. So that is a whole nother level of preparation to send astronauts. And also, I say like keeping them alive, it's not just like rationing food and that kind of thing, but having enough radiation protection to allow them to make that trip and come back, and to enable sort of like to not be a one-way thing is part of where things need to go next in order to enable humans, if we really wanted to be an interplanetary species, to enable us to even get boots on another world. Those are the first steps.
It occurs to me that they would be outside of the magnetic field of the Earth and therefore not protected from solar radiation. And in order to build a spaceship that has enough protection, they wouldn't be able to get it off the ground.
Yeah, you need a lead-lined
Yeah.
vehicle. So, but there have been like discussions about if you can use basically like biofilms, algal biofilms that would attenuate that radiation and allow humans to make the trip and irradiate, I guess, the algae instead. So there's a lot of in-space biomanufacturing and sort of like this concept of like leveraging those types of tools to enable longer-term spaceflight. It's a big thing.
Biofilms as protection from the solar wind. Interesting. One more question.
Got a very quick question. We saw the clear difference between the southern highlands and the northern lowlands. Does that mean that the northern lowlands at one time were a vast ocean? If so, how long do you suppose it took that ocean to vanish?
So that's one of the big questions, is whether there was an ocean, since we have so little on the ground coverage to give you sort of, I would say like, macro scale, geologic observations. Are there wave ripples that would tell you there's an ocean with waves lapping, right? Like, is there anything like that that indicates that you had water like that? We just don't have the observations to say yes or no because we have so few missions right there. But we know there was a ton of water, in these lakes and rivers I showed you today. That's a lot of water. It's got to go down. So we don't know with confidence. I think you probably had lakes to potentially an ocean at some point in the past. And again, with the when Mars dried up question, you're still talking about hundreds of millions of years, probably. But we don't know until we get samples back. And then we can have ages to go with those statements.
Well, thank everybody for coming, and thank you for a wonderful exposition. And
Thank you all so much. Thanks for being here.
I'm looking forward to watching it again on the ILR website, YouTube website. Thank you, everybody, for coming.
Thank you so much.